I audible? Yeah. So, good afternoon, all. I am Rashmi Sagar, second year PhD student in IIT Indore, and today I am presenting the initial results of uGMRT band 2 from deep observations. So, this is the overview of my talk. Firstly, I will talk about some introduction of epoch of reionization. Then I'll talk about the motivation behind my work and what are the challenges which we face in detection of 21 centimeter signal. What are the calibration processes we have used to calibrate the data of band 2, and then the results and images which we have received, and combined image which actually Professor Datta already shown in his talk. And then we have some results from the catalog. We have did the source classification and some initial results using TGE to the angular power spectrum. So this is the image which everyone has shown already and talked about what is the epoch of reionization. So I will just briefly tell. The epoch of reionization is especially the time when UV lights from first stars and galaxy of greater than 13.6 electron volt uh, uh, come and starts ionize the neutral hydrogen, and in the second in the oh, yeah in the second picture you can see the frequencies over the redshift 200 to the time when reionization has stopped. So there are several physical processes which is going in this time of period, which is like formation of first stars and galaxies, and heating, and the ionization process, which is mostly because of hydrogen gas. So the challenges there are several uncertainties in the exact form of this H121 centimeter signal, and apart from of these, there are different challenges which can be astrophysical challenges, in which mainly are foregrounds, which we'll talk later in this talk only. And then there are some instrumental challenges, and then there are some computational challenges also. So in foreground challenges, there are different kind of foregrounds, in which one of is galactic synchrotron radiation, which is the most dominant in all the foregrounds, and is due to the reason of the cosmic ray electrons uh, in our galactic is due to the magnetic field in our galaxy. And then there are synchrotron emission from the extended sources, which is because of mostly supernova remnants. And then there are free emission, which can be galactic and extragalactic, and there are point sources also. So here in this plot you can clearly see that how the foregrounds actually uh, overpower this 21 centimeter signal. So the motivation behind my work is to characterize this foregrounds, the property of those foregrounds, and the behavior at low frequency especially. So what are the reason we have chosen LIS and one field? So as Professor Datta already mentioned that it is multi-frequency field already, and and it is also on high galactic plane, which actually lowers down the galactic diffuse synchrotron emissions effect. And secondly is its transit time is at night time, which is actually better for us in terms of observation, because in night time the observations is less active. So and then about the previous work, we have already seen the last lectures on the last day by Samir Chaudhary and Srijita and Asif. They have already talked about the work done by Arnav Chakravarti in Band 2 in LIS N1 field, where he already performed direction dependent calibration and fitted the power law using the TGE. So here what we are doing new in this Band 2 is like we are approaching towards the direction dependent calibration, and we are also plotting the angular power spectrum using TGE, but we are also trying to use a clean PS, which I'm not showing here in this results, but in future we will also include those. Uh, so these are the observations in GMRT band 2 of the frequency of 200 megahertz with the usable bandwidth of 70 megahertz, and the total on source time is 17 hours. So these are the UV coverage of target LIS N1 field. Here on the left side you can see this is only one day data I have plotted to show this UV coverage before the flagging, and on the right side this is the complete data which we have received. Almost 30% data only we have remain in all 100% data after the flagging, and you can see that the UV coverage is not as much dense after most of the flagging in band 2, because there are lots of RFI also include as we go down in the observation at lower frequency. So we have here used the direction dependent calibration using the SPAM, which is source peeling atmospheric modeling, and it is based on AIPS, and in this SPAM, it contains two parts. One is pre-processing and second is the main pipeline. In pre-processing, the raw data, which is the LTA format, it converts into the pre-calibrated visibility files, and in the main pipeline, it has contained two parts also. Firstly, it did the direction independent calibration and then perform direction dependent calibration on those direction independent results. So here what is the benefit of this direction dependent calibration is it solves the ionospheric phase errors, which is not possible in direction independent calibrations, which can actually allow us the large field of view, and correction in ionospheric delay also improves the background noises and the flux scales in the lower frequency. So there are two different day images I have taken. In the left the day 1 and in the right the day 2. Here you can clearly see that the both day images have different one image has more noise in comparison to day 1, which I'll talk later. So firstly I will come to these significant artifacts, which you can clearly see in the red circles nearby these bright sources. These are mainly due to the residual phase errors, which is actually the reason in the direction dependent calibration errors. Like they are not able to properly perform the calibration to reduce these phase errors in the ionosphere, and resulting these significant artifacts, as you can see in both images. So as we zoom into the centers, if we just not see the bright source and just zoom into the center, we find that the RMS value of the left image is 225 microjansky per beam, whereas on the right side the image has almost 2 times of the RMS value. So these may be because of the different day has different ionospheric activities and an RFI, plus actually in second day image we find that there are some frequency chunks which are really bad, and when we were actually removing those frequency chunks, still the RMS noise will going increase. So we just include those all frequency in the second day, and then we found this a particular image for the second day. So every day data has a different situation, and one day data can be clean and another day data cannot be clean, and you can't do anything about it. So we have actually include all 3 day data and created this final image using WS Clean. Here you can see on the left side this complete image, and the central part of this image in the right side. So this is the main image where we have received the RMS value of 220 microjansky per beam at central frequency of 190 megahertz with the dynamic range of 7600 and confusion limit 29 microjansky per beam. So these are the montage we have created from this previous image, so that you can see that how particular some specific source look like in my image at 190 megahertz frequency. Here we have also shown LIS-N1 field at different frequency as it has been studied. So we have taken those frequencies also, the same sources. So you can see those same sources along with different frequencies. This is also the same, and so we have corrected this primary beam with the available updated primary beam coefficient from the GMRT. So this pipe, then we have generated the catalog also from this PyBDSF, where this PyBDSF actually generate the RMS noise map, which you can see on the left side. So in this RMS noise map, you can clearly see that in the field of view, the RMS noise is actually large on the places where there were bright sources, as I have shown in the red circles, those, and on the edges of the field of view, and on the right side the image of the area and the percentage of image with RMS noise, where when we go away from the center, the RMS noise increases. So we have also did the source classification from that catalog, where we have received 1317 sources, and in this source classification we have applied the condition from the Frazen et al. 2019 with this particularly formula, which is stands for separating the extended sources at 3 sigma level, and we have where sigma s and sigma s peaks are integrated flux uncertainty, and sigma s peak is peak flux uncertainty. So here we have received 435 resolved sources, which you can see in the pink color, and 882 are the unresolved sources or point-like sources in the violet color in this graph. And then we have also did the flux matching with other available catalogs. So flux matching we do mostly because we actually at different catalogs use different flux scales, and there could be uncertainties modeling in primary beam and systematic errors also. So for that we have matched our catalogs flux density with different catalog like LOFAR 150 megahertz, Sabitar et al. 2021, and Chakrabarti et al. 2019 400 megahertz, and GMRT 610 megahertz, which is Ishwara Chandra et al. 2020, and of course the VLA for survey. So we have also calculated the spectral index. So with the flux density we have received in our work. So here we have received the median of a spectral index of minus 1.1 for first catalog, and we have also calculated the astrometric accuracy in the position of the sources with the same catalog as we have compared for the flux flux scale offset. So here we have find the mean offset for this first survey, and 610 megahertz GMRT and 150 megahertz low far, where we have corrected our catalog on the basis of the first catalog. So like as I already mentioned that our main motivation is to precisely measure the galactic and extragalactic foregrounds. So here I have tried to actually uh, to measure this galactic and extragalactic foregrounds in terms of uh, angular powers to fit as the power law of angular power spectrum using TGE, which actually already briefly in detail has discussed by Dr. Samir Chaudhary and Srijita and Asif also. So I'm just coming to the results. So we have just chosen some frequencies in our data, and we have fitted the power law as a function of angular scale with this given formula, where we have found the values of A and beta, which you can see on the legend of this plot. And these are actually the initial results. We are still working with this TG and continuation. So to summarize, and for the future work, we have already performed the direction dependent calibration using SPAM, and we have produced the continuum image and created the catalog for source classification. For future work, we can study the individual sources also, and for the TG, we can produce angular power spectrum and use clean PS, and we are also welcoming for the collaboration. So if we can improve our result, we are really happy to do that. And we can use residual maps to store the H1 21 centimeter signal if possible with GMRT. So these are the references which we have taken for our this work, and thank you.
So thank you, Rashmi. Now we can have a few questions.
Yeah, this is really nice. Have you, by any chance, looked at the cylindrically averaged power spectrum as well, or
No.
do you have plans to look at that, or is there a reason you
As
don't want to do
I
it?
have mentioned that this is just initial works, and we are really open for the collaborations and all if possible, or we will definitely go towards the cylindrical power spectrum if possible.
Okay, thank you.
So few questions. This is 20-hour observation, is it?
No, 24 hours.
24. And how much is the flagging rate? Means data quality?
Actually, in 100% data, we have flagged almost 70% of data, left with 30% of data.
Oh, so this is the result for the 30% of the data. This is all the result using the 30% of the total, is it?
Yeah, for the TG, yeah, it is. But
No,
here,
for the imaging also, all these things, the result means how
yeah,
much
yeah.
RFI. Okay,
Yeah.
so 70% data is lost due to the RFI.
Due to the RFI.
Okay, in
In the
band
spam
2.
itself.
And another thing, can you go back to that? So this spam is used. This is apes based, correct? And image,
Yes.
all you have done in the apes or in the output from the spam package. So,
Actually, spam given us the continuum, the image in a visibility file, and then we have used this WS clean to concatenate all these visibility file as a one. So there we have only trial and error methods to get this the final image which I have shown here.
using the WS clean.
Yeah.
Okay, and another, that correction factor, the noise map you showed using, this is the output from the
Primary beam correction.
BDSF, correct?
Yes.
And what's the correction you are using actually? So this is for the DNDS calculation, is it? Or is
no, we haven't did DNDS calculation yet.
So what is the right panel then? Then how?
This is actually showing only that if we are moving from the center of the image to the outside, the RMS noise is increasing.
This is the area, is it? Why?
Yeah, this is the area of the image, and this is the percentage of the image, how it's increasing, and this is the RMS. Like you would clearly see that the RMS noise is increasing as you are going from the area as area is increasing, and the
Okay.
percentage of the
Okay. Okay, great. Thanks. Yeah.
The final image you showed, so some of the point sources still shows quite a bit of artifacts around it, right?
Yes,
If you go to the final image.
yes,
So I presume that these are direction dependent calibrated already.
yes, yes. We
So-
are also.
So these are
assuming that.
still, after that, you still see these artifacts.
Yeah, as I mentioned that we have did the trial and error in WS Clean as much as possible to change like less less RMS noise. So these are still the artifacts which we have left. So we are also assuming that these are only the direction dependent calibration errors which we can't remove.
And so what is the weighting that you used? Robust factor.
-1. Yeah.
AO flagger or the
No,
SY?
AO flagger will actually. I had a plot where I have like earlier shown. Right now, I don't have. But what it is like when there is a data at particular 180 frequency, it is flagging that also. So that so AO flagger is not usable for especially the band 2 data.
Which you used by hand?
Yeah, I have plotted this in that RFI GUI to just see that how the effect of AO flagger will come.
So that means using CASA or something, is it?
Like directly AO flagger, I have also used in our data where it has like flagged almost 90% of the data.
Okay.
So it is not that much useful.
Okay, yeah.
Yes.
So you have achieved the RMS of 220, but what's the best expectation? The theoretical.
In GTech of GMRT, the best results are 500 microjansky per beam.
Okay, now the theoretical value of RMS. I mean, what's the best you can get in principle?
That will be that currently I can't remind.
Okay. Oh, thanks.
Calculate.